as I've said before, isomap, also MDS. MDS is multidimensional scaling. Isomap uses shortest path and then uses classical MDS. So it is meaningful to talk about MDS, which is very related to first ideas in metric embedding in the context of machine learning, not in the context of pure mathematics and applied mathematics. Just in the context of machine learning, people know MDS. So metric embedding is MDS is very, very related to these formulations, multidimensional scaling. So it measures, it preserves the similarity between samples by projection, and so we move from XY to new feature space, X prime and Y prime. When we have X and Y, it preserved pairwise distance, and it gives X prime and Y prime. So it's a good method for information visualization since we reduce to 2 or 3 dimensions. So in MDS, we minimize the square difference for the pairwise distance between all training data and projected, which is lower dimensional case. So we define stress of x1 through xn. We define a stress to be the sum from I from 1 to n, j from 1 to and xi minus xj minus delta ij, which is the similarity in the original space. And this is the similarity in the projected space. And then this one, so the classical, let's say the classical MDS is as follows. First, we calculate the squared distances, delta ij, and then we apply double centering. Let's say B, and then we solve for eigenvalues lambda 1 through lambda p and eigenvectors v1 through vp, where p is your required number of dimensions. And finally, we solve for the projected coordinates. So x prime is now EP lambda p square root. And so this one is a diagonal eigenvalue matrix, and these are your eigenvectors. So the metric MDS we should minimize the stress. And let's talk about the distance function. The distance function, first, the distance between x and y we want to go from similarities to dissimilarities. First, in a metric, x and y is positive, the distance between them. And if the distance is 0, it means that it is the same point, and d of x and y is d of y and x. And finally, the triangular, which we use it in metric embedding to prove that our distortion is good enough, which is less than the sum of dxy and dyz. So in this context, PCA could be deemed as a simple form of MDS. And PCA does not seek to directly preserve pairwise distances. And I've said earlier that, we don't talk about distortion when we talk about PCA and LLA and many classical results in machine learning. So let's go from similarities to dissimilarities to see the beautiful relationship. So we can write this squared as a sum of. So we can write dxy squared as multiplication of x minus 1 and times x minus 1, which is equal to x times x minus 2 x times y plus y and y. So this one is just sx and y. So we can rewrite it and say sx and y is equal to 1 over 2 minus dx and y squared plus So let's talk about random projections again. So x random projection, which is p by n, is R, which is a random projection, p is the reduced dimension, and m is the features size, times x m by n. N is the number of samples, and m is feature. So in large dimensions, R transpose R is nearly identity. And the interesting thing about JL Lemma is that points in high-dimensional space can be linearly embedded in a space of much lower dimension, such that the distances between the points are nearly preserved. So this phi x minus 1 is between 1 plus epsilon distortion and 1 minus epsilon distortion. In PCA, which is not scalable, also it is not robust, even if you use robust PCA, is of order of m to n because you're using the covariance, and then you use eigenvalue decomposition, so m cube, and then nmp because you're doing projection after that. But in random projection, you use only projection, so that's why the order of complexity is much less. So we use it for real-time data that we don't have all the data in advance. And the interesting things that some people use a JL Lemma and instead of working on JL, they work on RIP, which I will talk about it, which is restricted isometry property. This is restricted isometry property. And the proof is for using epsilon net is so simple. This direction is very efficient. But this direction, you lose factor log n. So restricted isometry property is easier, but JL is better. I want to talk about also you need it's a prerequisite, so I should talk about it. Kmeans, that which objective you need to choose. So Kmeans is a MP hard problem. It's a combinatorial optimization problem, and it is developed by Tipshirani, Hasty, and Friedman, which they minimized K from K because we have K-means and K clusters. So Xi minus Mk, M is the class mean. They minimize this. So we have X1 through Xn, and each of them is Rd. We start, so the algorithm is this. So the algorithm for K-means is that we start with M centers. We assign all points to closest cluster center, and then we define new clusters as the mean vector of the current clusters. The problem is that it ends in local optimum, and everybody knows that. So the solution depends on initialization. Another approach to clustering is hierarchical clustering. And this algorithm could be used for metric learning. In the context of when you want to embed it into an ultra matrix, you understand what I mean. So you consider a dendrogram, which people use in financial markets very much to select some assets. And then, so it's like this. So you go to the finest granularity. So each point in its own cluster. We check which points are closest and merge them to form a new cluster. And always merge two closest clusters until we are left with only one cluster. And so also we need to know what is the distance between C and C prime. So this is minimum of d of x and y if x is in C, if y is in C prime. This is a single linkage. But also we have average linkage. Average linkage is that the distance between two clusters are dx and y for x in C and y in C prime, the cardinality of C times the cardinality of C prime. And we also have a complete linkage. So the distance between C and C prime is the max for any x in C and y in C prime. So when you want to go from a true degree function to empirical degree function, so this is true degree function, you can define it by this kernel dpy, which is in C of x, but the empirical distance, the n of x, which we use in practice, is kx and y dp n of y, which is in C of x. So we can define the normalized empirical similarity function, which is hn of x and y. This one is equal to k of x and y divided by the n of x, the n of y. And same true for true similarity function, which is k of x and y divided by square root of d of x, d of y. So what is that restricted isometry matrices property that I said? So restricted isometry matrices, or RIP, you can view it as a matrix M. So you project it and go to a lower space, but this time you have the projected element. The projected element, the length of that should be between 1 plus delta x squared and 1 minus delta x squared. And you know that m is less than d. So the key result is that m is just order of k log d or k. So designing deterministic matrices M that have RIP in polynomial time is still an open question. That's why most people use probabilistic approaches. So modern popular choice include matrices where entries are IID Gaussian or Bernoulli variables. So M from E to F. So this has norm E and this has norm in F. These are semi-norms. So in semi-norm, when I say semi-norm, it means that it need not to be positive definite that for any x, if p of x is 0, x is equal to 0, we don't need this condition. So it's a semi-norm. So semi-norm can be classified in terms of absolutely convex absorbing subsets A of X. So we say gauge of A is PA of X. This is like that gauge that Minkowski used many years ago, which is the infimum of R, where R is greater than 0 and X is in RA. I'm not sure if that is gauge, but this is gauge as well. So Kolmogorov says that only locally convex and locally bounded topological vector space is normable. So the definition of a lower restricted isometry property is somehow saying that. So let's say What do I mean by